Somewhere beneath your feet, right now, there is magma. Not deep in some abstract geological sense. Not millions of kilometers away. Magma, liquid rock, superheated to over 1,000 degrees, sitting in chambers and reservoirs that stretch for dozens of kilometers in every direction, held in place by nothing more than the pressure and temperature of the rock around them. Most of the time, this system is stable. It has been stable for thousands, sometimes millions of years. But stable does not mean permanent, and in 2026, something is changing. Beneath a city of 3 million people in southern Italy, the ground is rising. 10 millimeters per month, 70 earthquakes in a single week, sensors recording a system that, by every measurable indicator, is accelerating. Beneath Wyoming, a new study published in the journal Science has revealed that one of the most watched volcanic systems on Earth is more complex, more dynamic, and holds more magma closer to the surface than models assumed for decades. And in Indonesia, the site of the largest eruption in the last 2 million years, an event that may have reduced the entire human population to fewer than 10,000 people. Scientists are watching a system that has never fully gone quiet. These are not isolated curiosities. They are a set of interconnected warnings from a planet that has been trying to tell us something for a very long time. This is what scientists are paying attention to, and why, in 2026, they are paying more attention than ever before. Before we talk about the specific supervolcanoes that concern scientists most, we need to establish what separates a supervolcano from an ordinary volcano. The distinction is not just one of size, it is one of category. A conventional volcanic eruption, even a large one, ejects material measured in cubic kilometers. The 1980 eruption of Mount St. Helens in Washington state ejected approximately 1 cubic kilometer of material. It killed 57 people, flattened hundreds of square kilometers of forest, and disrupted air travel across the Pacific Northwest for weeks. That was a large eruption by any ordinary standard. A supervolcano is defined by the threshold of 1,000 cubic kilometers of ejected material in a single event. To put that in perspective, a supervolcanic eruption would need to be at least 1,000 times larger than Mount St. Helens. The 1815 eruption of Tambora in Indonesia, the largest volcanic event in recorded human history, ejected approximately 160 cubic kilometers. It killed an estimated 71,000 people directly. The ash it sent into the stratosphere blocked enough sunlight to cause global temperatures to drop by more than a degree. 1816 became known across Europe and North America as the year without a summer. Crops failed. Famine followed across multiple continents. The death toll from the aftermath reached hundreds of thousands. Tambora was not a supervolcano. It was approximately 6 times smaller than the minimum threshold. A true super eruption would be categorically different from anything in recorded human history. The pyroclastic flows alone, superheated gas and rock moving at hundreds of kilometers per hour, would devastate regions the size of small countries. Ash would fall across entire continents, destroying agriculture on a scale that would trigger famine not in individual nations, but globally. The sulfur dioxide injected into the stratosphere would reflect sunlight for years, dropping global temperatures by several degrees and potentially collapsing growing seasons across the northern hemisphere for a decade or more. Scientists call this a volcanic winter. The last one occurred 74,000 years ago, and what happened then should give us pause. 74,000 years ago, in what is now the northern part of Sumatra, Indonesia, A supervolcano erupted. We call it Toba. Nearly 3,000 times more than Mount St. Helens. The ash cloud it produced has been found in sediment records across South Asia, the Middle East, and East Africa. Microscopic glass particles from the eruption, called cryptotephras, have been identified at sites thousands of kilometers from the blast. The sky darkened across the planet. Global temperatures fell by somewhere between 3 and 5 degrees Celsius. In the northern hemisphere, the cooling may have been more severe. Some models suggest up to 4 degrees below the already cold temperatures of an Ice Age world. Ecosystems that had taken thousands of years to establish were disrupted within years. Forests thinned. Food chains collapsed. For decades, scientists have debated what this meant for our species. The Toba catastrophe theory, developed in the 1990s and early 2000s, proposed that the eruption drove the global human population to fewer than 10,000 individuals. The evidence was in our DNA. Modern humans carry remarkably little genetic diversity compared to other great apes, suggesting that our entire species passed through a severe bottleneck. A period when the population was so small that most of the genetic variation that existed before was simply lost. Toba and the volcanic winter it created was the most obvious suspect. The emerging science in 2025 and 2026 has complicated this picture in ways that are, if anything, more interesting than the original theory. Archaeological evidence from sites in Africa, India, and China has shown that human communities survived near the blast zone and continued to make tools, adapt their behavior, and innovate in the years following the eruption. Research published in 2025 found that the effects of Toba were not experienced evenly across the globe. The southern hemisphere showed little to no cooling in some models, and populations in Africa may have been far less severely affected than those in the north. The emerging consensus is nuanced. Toba was catastrophic, but humans were more resilient than the original theory suggested. We did not go quietly. We adapted. We innovated. We survived. But here's what that nuanced picture does not change. A super eruption of that scale still collapsed ecosystems across half the planet, still darkened skies for years, still dropped temperatures enough to devastate agriculture, in a world where agriculture had not yet been invented. Early humans were hunter-gatherers. They could move. They could adapt their diet. They had flexibility that agricultural civilizations do not have. A volcanic winter today, striking a world of 8 billion people, almost all of them dependent on global food supply chains, on predictable growing seasons, on agricultural infrastructure that cannot simply pick up and move, would be categorically more devastating than anything Toba inflicted on our ancestors. That is not a reason for panic. It is a reason for the kind of serious scientific attention that, in 2026, is finally being directed at the right places. The supervolcano that commands the most public attention is Yellowstone, and the science around it in 2026 is genuinely more interesting and more unsettling than the reassuring headlines that usually accompany it. Yellowstone sits atop a hotspot, a plume of unusually hot mantle rock rising from deep within the earth and punching through the overlying crust. It has produced 3 super eruptions in the last 2.1 million years. At 2.1 million years ago, 1.3 million years ago, and 630,000 years ago. The caldera visible today, a depression roughly 72 by 55 kilometers, was formed by that most recent event. For years, the standard scientific characterization of Yellowstone was reassuring. The magma chamber beneath it is only 5 to 15% molten. The system releases gases continuously, which helps relieve pressure. The annual probability of a super eruption, according to USGS estimates, is approximately 1 in 730,000. Those facts remain true. What changed in April 2026 was the model. A study published in the journal Science by scientists from the Chinese Academy of Sciences produced a comprehensive three-dimensional model of the magmatic system beneath Yellowstone and found that it operates differently from what previous models assumed. The magma is fed not by a single deep reservoir, but by a system that draws from closer to the surface than expected, driven by tectonic forces that previous models had underestimated. The researchers were careful. They did not claim Yellowstone is about to erupt. The probability assessments remain the same, but what the study revealed is that the underground system is more complex, more dynamic, and more extensive than the scientific community had previously modeled. The magma is not sitting inertly in a simple chamber. It is being actively fed, actively moving, and actively influenced by forces that science is only now beginning to map with the resolution required to understand them. In early 2026, ground deformation sensors at Yellowstone detected a 19-mile bulge, a dome of rising ground caused by the movement of magma approximately 9 miles below the surface. Scientists noted that if eruption were imminent, the deformation would be much shallower and more dramatic. This particular bulge is consistent with normal magmatic breathing, the kind of movement that has characterized Yellowstone for as long as instruments have been watching it. But it is a reminder that this system is not static. It is breathing. It is moving. And our understanding of exactly how it breathes has just been fundamentally revised. If Yellowstone is the supervolcano that commands the most public attention, Campi Flegrei is the one that commands the most scientific urgency right now. And in June 2026, the numbers coming out of Campi Flegrei are not reassuring. Campi Flegrei, Italian for burning fields, is a caldera system located on the western edge of Naples in southern Italy. It is not the dramatic cone-shaped volcano of popular imagination. It is a depression 12 by 15 kilometers across, much of it beneath the Tyrrhenian Sea, with scattered craters, fumaroles, and volcanic vents spread across what looks, from the outside, like ordinary landscape. 500,000 people live inside its caldera. 3 million more live within direct hazard range. The system last erupted in 1538, a small eruption that built a new hill, Monte Nuovo, in 48 hours and killed a small number of people. Before that, its last major eruption was 39,000 years ago, when it ejected 300 cubic kilometers of material in an event that some researchers have linked to the extinction of the Neanderthals across Europe. Since 2005, Campi Flegrei has been in a state of accelerating unrest. The ground has risen by more than 1 meter since measurements began, a phenomenon called bradyseism, caused by the movement of magma and superheated hydrothermal fluids beneath the caldera. In the week of February 23rd to March 1st, 2026, seismographs recorded approximately 70 earthquakes, with magnitudes up to 3.5, concentrated beneath Pozzuoli and the Agnano area. The following week recorded 47 additional earthquakes. This is elevated, significantly elevated. A 2026 paper published on Arco modeled the current trajectory of ground deformation and seismic activity and projected that the system could reach what researchers called a critical mechanical threshold between 2030 and 2034. The authors were explicit that this does not necessarily mean eruption. It could mean a regime change, new fractures opening, increased fumarole activity, localized ground failure, without a full volcanic event. But it could also mean something more. The scientific consensus, as summarized by Italy's National Institute of Geophysics and Volcanology, is clear. Campi Flegrei is more active than it has been at any point in the modern monitoring era. The trajectory is accelerating, and a separate 2025 paper in Nature Communications concluded that seismic risk mitigation, specifically the retrofitting of buildings within the caldera, is the most effective immediate strategy, regardless of whether an eruption occurs. That recommendation matters because in an area of high volcanic unrest, earthquakes alone, without any eruption, can cause catastrophic structural damage to buildings that were never designed to withstand them. The question of whether Campi Flegrei is more dangerous than Yellowstone has a specific answer that depends entirely on what you mean by dangerous. Yellowstone's caldera is physically much larger. Its largest eruptions were VEI-8, one full order of magnitude above Campi Flegrei's VEI-7 maximum. In terms of global consequence, a Yellowstone super-eruption would be more catastrophic than anything Campi Flegrei could produce. But Yellowstone is in a sparsely populated corner of Wyoming. Its last eruption was 70,000 years ago. Campi Flegrei has 3 million people within direct hazard range. It is actively accelerating, and its last significant, somewhere beneath your feet, right now, there is magma. Not deep in some abstract geological sense, not millions of kilometers away. Magma, liquid rock, superheated to over 1,000 degrees, sitting in chambers and reservoirs that stretch for dozens of kilometers in every direction, held in place by nothing more than the pressure and temperature of the rock around them. Most of the time, this system is stable. It has been stable for thousands, sometimes millions of years. But stable does not mean permanent, and in 2026, something is changing. Beneath a city of 3 million people in southern Italy, the ground is rising. 10 millimeters per month, 70 earthquakes in a single week, sensors recording a system that, by every measurable indicator, is accelerating. Beneath Wyoming, a new study published in the journal Science has revealed that one of the most watched volcanic systems on Earth is more complex, more dynamic, and holds more magma closer to the surface than models assumed for decades. And in Indonesia, the site of the largest eruption in the last 2 million years, an event that may have reduced the entire human population to fewer than 10,000 people. Scientists are watching a system that has never fully gone quiet. These are not isolated curiosities. They are a set of interconnected warnings from a planet that has been trying to tell us something for a very long time. This is what scientists are paying attention to, and why, in 2026, they are paying more attention than ever before. Before we talk about the specific supervolcanoes that concern scientists most, we need to establish what separates a supervolcano from an ordinary volcano. The distinction is not just one of size, it is one of category. A conventional volcanic eruption, even a large one, ejects material measured in cubic kilometers. The 1980 eruption of Mount St. Helens in Washington state ejected approximately 1 cubic kilometer of material. It killed 57 people, flattened hundreds of square kilometers of forest, and disrupted air travel across the Pacific Northwest for weeks. The absence of an eruption in the modern era tells us very little about what the next 1,000 years will bring, let alone the next 10,000. What scientists are increasingly focused on is not prediction, it is preparation. The evacuation of 3 million people from the Naples region around Campi Flegrei has been studied, modeled, and found to require at minimum a week of advance warning to execute without catastrophic loss of life. Whether Campi Flegrei would provide a week of warning or hours is one of the open questions that current monitoring is designed to answer. Research published in 2025 on past eruptions at Toba suggests that warning signs could be minimal, that the system could move from unrest to eruption faster than models had assumed, that the geological record shows previous eruptions that were preceded by shorter, smaller signals than scientists had hoped for. That finding, from Toba specifically, is what makes the monitoring question so urgent. The hope has always been that supervolcanoes would give us years of escalating warning before a major event. The evidence from Toba suggests that hope may not always be warranted. There is a strange kind of perspective that comes from studying supervolcanoes seriously. On one hand, the probability numbers are genuinely reassuring. The chance of a super eruption in any given year is extraordinarily small. These systems operate on geological timescales that dwarf the entirety of recorded human history. On the other hand, the consequences of a super eruption, a real one at the scale of Toba, are so far beyond anything in human experience that our entire framework for thinking about risk struggles to accommodate them. We have no word for a disaster that kills hundreds of millions of people, darkens the sky for years, and collapses global food systems simultaneously. What we do have is science. Satellites that can detect ground deformation measured in millimeters per month. Seismograph networks that can distinguish between ordinary tectonic movement and the specific signatures of magma migration. Geochemical sensors that can analyze the composition of volcanic gases and infer what is happening in the chambers below. In 2026, Campi Flegrei is rising 10 millimeters per month. Yellowstone has revealed a magmatic system more complex than its models assumed. Toba sits quiet over a system that last produced the largest eruption in 2 million years. Scientists are not panicking. They are watching. They are measuring. They are building better models and asking harder questions. That is the correct response to systems that operate on timescales longer than human civilization, but carry consequences large enough to reshape it. The Earth has always been this way. We are simply finally beginning to understand it well enough to take it seriously. This is Terrum.